Sampling distribution of the sample mean. Consider a random sample of quantitative, not categorical data. In this case, we have a sample size n of measurements, numbers with units, and we study the sampling distribution of the sample mean. Recall that a sampling distribution is the behavior for a statistic when you observe all possible samples. Consider this process. Take a random sample of n data values, quantitative in this case. Calculate the sample mean, which we call y bar. Repeat these two steps many times. In theory, you'd examine all possible samples for that sample size n. Suppose I did this and obtained 100,000 values for y bar. Are there certain patterns I would observe if I made a histogram of these 100,000 values? Now, in each experiment, there's some, usually unknown, population distribution, which we have a population mean denoted by mu and a population standard deviation denoted by sigma. Further, we take a sample of some number n values. Now, the sampling distribution of the sample mean remember, for sampling distributions, I want to know first, where is it centered? Second, how spread out are the values? And third, does it look close to a normal curve? So let's look at these results. 1. The center is defined as mu sub y bar, which is the mean of all possible y bar values, and is equal to the mean of the population from which you are taking the sample. So 1, center, mu sub y bar equals mu, can be written. 2, the variability is written as sigma sub y bar and represents how spread out or how variable all the y bar values are. It is the ratio of the spread in the population, which is sigma, to the square root of the sample size n. This can sometimes be called the standard error of the mean or the standard deviation of the y bar or the mean distribution. Notice there are two things that can sound similar here. There's a sigma, which represents the original variability of the individual numbers in the population from which you're drawing the sample, where now I'm saying standard deviation of y bar to describe how spread out the y bar values are themselves. Be sure you pay careful attention to the differences between sigma and sigma sub y bar. Third, we want to know if we can approximate the distribution using a normal curve. To do this, you need to have a random sample of quantitative data, and either the original population must have a normal distribution, or the sample size must be sufficiently large. By sufficiently large, we will say that if n is 30 or more, that is large enough to treat the sampling distribution of the mean like a normal distribution. This actually comes from what is called the central limit theorem, which essentially says that when you take sample means, the more data you use to calculate each mean, the sample size n, the closer the sampling distribution, or think histogram of all possible y bar values, will look to a normal curve. To have a value that is large enough of a sample size, in most cases 30 or more values used to calculate the sample mean, the y bar value, works well. If these normal conditions are met and we can treat the distribution like a normal curve, then we can calculate z-scores using the formula z equals y bar minus mu over sigma over the square root of n, or y bar minus the mean of all y bars over the standard deviation of y bars. We can use table Z to find probabilities. But note, you must know the value of the population standard deviation, sigma, to use this formula. Fully describe your sampling distribution first. This includes the mean, the standard error of the mean or the standard deviation of the mean distribution, and whether the curve is well approximated by a normal curve. After you've concluded a normal curve is appropriate, then you can proceed by creating a z-score and calculating a probability. If the normal curve is not appropriate, you would stop and just make a statement that the normal approximation is not justified. For example, suppose you take a random sample of 49 weights from a population of sophomore males where the mean is 150 pounds and the standard deviation is 14 pounds. What would the sampling distribution look like? Start by writing down what you know about the population. The mean is 150 pounds. The standard deviation of individual weights is 14 pounds, and the sample size is 49. Then the sampling distribution can be described where the mean is mu sub y bar, which equals the mean of the original population, where mu is 150 pounds. The standard deviation of the y-bar distribution, is sigma sub y bar, which is sigma divided by the square root of n, so that is 14 divided by the square root of 49, which is just 7. So 14 divided by 7 is 2 pounds. Now a random sample of quantitative data, these weights, was taken from the population, and the sample included n equal to 49 values, and that is at least 30, so this is considered sufficiently large. Hence, the sampling distribution of the sample mean is well approximated by a normal distribution that has a mean of 150 pounds, and the standard error or the standard deviation of the mean distribution would be 2 pounds. Visually, sketch the sampling distribution by drawing a normal curve, labeling the mean in the center at 150 pounds, and then 3 standard deviations of the mean on each side of that center. So that would be 150 minus 3 times 2, so 150 minus 6 is 144 pounds. And similarly, the mean plus 3 times the standard deviation of the mean is 150 plus 3 times 2, or 150 plus 6, which is 156 pounds. This is where you would begin with this material. Be sure you can get this sketch, and then your next step would be to actually find a probability.